Good afternoon. First of all, a big thank you to Ivana and Liborio for inviting me to participate in this exciting symposium. It is a true honor and pleasure to do so. Now, let me share my presentation. Okay. So when REM sleep was first described by Zarinsky and Kleitman in 1953, they were quick to notice that if you awoke someone from the sleep stage and asked the person whether he or she had a dream, the answer was yes, in 74% of cases, compared to other periods without ocular movement, where it was only 8%. And so it was quite natural that they concluded that they had found a method that furnished the means of determining the incidence and duration of periods of dreaming. This discovery made a lot of sense, considering the electrophysiological hallmarks of REM sleep, rapid eye movements, as if someone was looking at an animated scene, but also activated EEG, and as later shown by Jouvet, muscle atonia that prevented the enactment of dream-related movements. This discovery also has to be seen in the context of a time. Dream studies were heavily influenced by psychoanalytic Freudian theories that lacked any experimental evidence. And so I can only imagine the excitement of finally discovering an objective correlate of dreaming that was considered something very, very subjective at the time and not amenable to scientific research. And in the subsequent years, it was confirmed that the incidence of dreaming was very high during REM sleep, and several studies describing the phenomenology of dreamings and dream contents were conducted, and there was even a coding system that was established to code dream reports and to systematically study dream contents, like the one of Halle van der Kaste, which has been very influential and which is still used today. Several content studies also confirmed the relation of dreams to specific characteristics of rapid eye movement sleep, like, for instance, eye movements that were initially shown to correlate in their direction with the localization of dream percepts, but also the discovery that dreams were largely unrelated to sensory stimulations in the environment. In this experiment, Rechtschaffen and Fuchs showed several objects to participants that had their eyes taped open while they were in REM sleep, and these participants subsequently reported that they dreamt of different things than the objects that were shown to them. So this is an important study because it clearly described that dream is a state in which one is disconnected on the sensory side from the environment. Subsequently, REM sleep was characterized also in neuromodulatory terms and neurochemical terms, if one may say so. So REM sleep was shown to be strongly influenced by high cholinergic tone and to be inhibited by high noradrenergic tone, and that these two neuromodulator systems influenced each other reciprocally. And this discovery was at the basis of one of the very influential theories on the mechanisms underlying dreaming, in which the brainstem plays a major role, excites sensory regions, including visual areas. And according to this theory, other cortical areas, including the frontal lobe, then try to incorporate these activations into a more or less coherent dream plot. With the area of functional neuroimaging, the possibility to image regional brain activations during sleep emerged, as shown here for REM sleep by Maquet and colleagues. And taken together, these studies have shown that REM sleep, as opposed to wakefulness, for instance, is characterized by relative frontal deactivation, and that has been interpreted to underlie, for instance, a lack of control and judgment than one has in dreams, but also that REM sleep is characterized by very high activity in visual associative areas that have been put in relation with the hallucinatory character of dreams, and also with a very strong activation of limbic circuits, which has been thought to reflect the affective properties of dreams. The study of functional imaging underlying REM sleep and dreaming has been taken a step further, also by studies using TMS EEG to probe effective connectivity during sleep that, according to prominent theories of consciousness, is a prerequisite for consciousness. And so here in this series of study, it was shown that effective connectivity breaks down in slow wave sleep, where consciousness is most likely to fade within sleep, but is preserved in REM sleep, where consciousness is present in the form of dreams. Now, in the studies that I've shown, REM sleep is used as a proxy for dreaming, and perhaps you've seen from the titles that these two terms are used interchangeably. But is this really the case? The answer is no. And as I will show in subsequent studies, dreaming can be dissociated from REM sleep. That's one of the major changes that has emerged in the conceptualization of dreaming. And this is supported by, for instance, lesion studies showing that lesions of the forebrain can lead to a global cessation of dreaming while leaving REM sleep intact. And the other way around, you can pharmacologically abolish REM sleep without affecting dreaming. And we also know that dreaming can occur in non-REM sleep, even if there has not been any prior REM sleep, like for instance, during naps, as shown in this study here. And I like to show this graph showing the incidence of reported incidence of dreamings for REM sleep across the years from the 1950s to 1990s, prepared by Nielsen, that shows a relative stability for REM sleep, very high incidence, around 80%, and almost linear increase for non-REM sleep, reaching 60% in the 1990s. Now, what is behind this increase, this apparent increase of dreaming? It's not a real increase, but very likely that it has to do with the way researchers assess dreaming, with the way they formulated the questions, going from did you just have a dream to what was going through the mind, so more open-ended question. And with this, one can capture a larger variety of conscious experiences during sleep. And while there may be clear quantitative differences and perhaps less clear qualitative differences, I think it's now very well established that dreaming can occur in non-REM sleep. And in some instances be not distinguishable from REM sleep. And so obviously this has puzzled researchers. How can dreaming occur in two behavioral states with radically different global EEG signatures? REM sleep, low amplitude, high frequency EEG, and non-REM sleep, high amplitude, low frequency EEG. And here there has been a paradigm shift in the last decades from a global to a local view of sleep. We've known for a long time that animals can have unihemispheric sleep. Some animals, like dolphins, humans, do not have this. But the physiological hallmarks of non-REM sleep, like slow waves and even the associated periods of neuronal silence in thalamocortical neurons, are not equally distributed across the cortical mantles. And adults, slow waves, for instance, are much larger in the front than in the back. And they also depend on processes like learning. And we also know that slow waves and the periods of neuronal silence that accompany them do not only locally occur in non-REM sleep, as shown here in a study using intracranial recordings, but can also be present locally in REM sleep, and even in conditions of sleep deprivation, intrude into wakefulness, where they directly related with functional impairment. And so what has this implied for the study of dreams? Well, to capture these local patterns, it became necessary to record brain activity with a high spatial resolution, in addition to the temporal resolution of EEG. going from representations of brain activity like this one, traditional conventional EEG, to brain activity maps like these ones that can be obtained using techniques like high density EEG with source modeling, or EEG fMRI, or also other techniques. And also it has meant that it became necessary to probe dreaming within states. So instead of using REM sleep as a proxy of dreaming and slow wave sleep as an proxy for an absence of dreaming, it became necessary to probe dreaming within states and to compare dreaming and no dreaming within states, because we know that they can occur within the same state. And so this type of technique has led to the description of neurophysiological signatures that are common to both REM sleep and non-REM sleep, like, for instance, the activation in posterior cortical regions, but also the descriptions of EEG activations corresponding to specific dream contents, perceptual dream contents, like, for instance, faces or speech, that correspond very well to the activations that are seen when the same contents are perceived in wakefulness. Similar correspondences between wakefulness and dreaming have been shown for movement. For example, dreamt movement in lucid dreams activates sensory motor regions, or fear, dreamt fear, that activates limbic regions in both non-REM and REM sleep. And then in the last few years, there has been a development of course, AI techniques that will likely play a major role also in the future of dream studies. Here, for instance, a study 10 years ago in which decoder trained on waking fMRI data acquired during perception while participants watched movies was used to predict dream contents at sleep onset, while participants in the scanner were transitioning towards sleep. And just an example to show you that it was read how it worked and that it was really successful. Here's a movie showing at any given instant across time what the computer is predicting that the participant is dreaming of. You can see that character emerges here as the most prominent prediction. And here the participant is woken up, asked what he or she had been dreaming about. And this is the answer, that it was indeed characters as predicted by the algorithms in black and white as the only thing that was there. So what have we seen? We have seen that since the discovery of REM sleep, of its electrophysiological descriptions in the 1950s, there has been a major neurochemical, neuroanatomical, functional refinement of the state. And we have moved from a view that is relatively state dependent of dreaming, dependent on REM sleep, and also brainstem heavy, to a view in which dreaming is thought to occur throughout sleep, and also heavily depends on the cortex. And I think despite these major advances, the big questions surrounding dreaming remain open. Where do dreams originate? What determines dream contents? How does dreaming relate to the functions of sleep? And do dreams serve a function? And I hope that this really will serve as a motivation for researchers to go into this field. So with this, again, big thank you. And also thank you for the attention.